this integration. The path of integration, normally integral a to b f of x dx is always along the x-axis from x is equal to a to x is equal to b in the case of a real variable. But in the case of a complex function f of z, the path of the definite integral a to b f of z dz can be along any curve from z equal to a to z equal to b. Its value depends upon the path of the integration. Now, what is meant by the connected region? Whenever the 2 points of the region are connected by a curve, and if it lies entirely inside the region, then R is said to be connected. Now, simply connected region. A region R is said to be simply connected if any closed curve which lies in R can be shrunk to a point without leaving R. A region which is not simply connected is said to be multiply connected. So this is called a simply connected region because the outer circle and inside you have another circle, so it lies entirely within the region. Now this is called a multiply connected region. Here you have two more curves that lies inside the big circle. And this multiply connected region can be converted into a simply connected region just by drawing strip cuts like this. So the first circle is connected to the second circle just by drawing the cuts. Now the second one connected to the bigger one, drawing the strip cuts like this. Therefore, whenever we start from the circle inside and we can move around, and therefore it can end. So it can be converted into a simply connected region just by drawing the cuts, strip cuts. Now coming to the theorem, Cauchy's integral theorem states, and this is also called as Cauchy's fundamental theorem, if f of z is analytic at every point of the region R bounded by a closed curve C, and if f dash of z is continuous at all points inside and on a simple closed curve C, then integral over C f of z dz equal to 0. Here we have to note that whenever the function f of z is analytic at all points inside and on a closed contour C, then the value of the integral is equal to 0. That is, the integral over C f of z dz equal to 0. Now, Cauchy's integral formula states that if f of z is analytic within and on the closed curve C of a simply connected region R, and if A is any point in the interior of R, then f of A is equal to 1 by 2 pi I integral over C f of z by z minus A dz, where the integration is around C is in the positive sense. That means that the integration is in the anti-clockwise direction. Now let us see some problems. Evaluate using Cauchy integral formula, integral over C, z plus 1 divided by z square plus 2z plus 4 dz, where C is modulus z plus 1 plus I is equal to 2. Let us consider this integrand function as f of z, that is equal to z plus 1 by z square plus 2z plus 4. The function f of z will be analytic by finding the singular points just by equating the denominator to 0. Now equating the denominator to 0, this will become a quadratic equation, and by using the formula z equal to minus b plus r minus root of b square minus 4ac by 2a. A is the coefficient of z square, which is equal to 1. B is equal to the coefficient of z, which is equal to 2, and C is equal to 4. So substitute in the formula, therefore we get z equal to minus 2 plus r minus root of b square. So 4 minus 4 into A is 1, C is 4. So 4 into 4, 16. So simplification, we get z equal to minus 1 plus r minus I into root 3. Because minus 16 plus 4 will become minus 12, and minus 12 can be written as 4 into 3. So taking root 3 outside, and minus I will become minus 1 will become I square, and therefore taking from the square root will be getting 2y. So taking 2 common, we can cancel 2, and therefore we will be getting z equal to minus 1 plus or minus I into root 3. So these are the two singular points. Now substituting these two singular points in the given curve, modulus z plus 1 plus I is equal to 2. So this is a circle equation with the center. This z can be taken as x plus iy. So the real part will be x plus 1, imaginary part will be I into y plus 1. So x is equal to minus 1, y is equal to minus 1 is the center of the circle, and radius of the circle is 2. Therefore the boundary of the region is minus 2 to plus 2. Now substituting the first singular point z equal to minus 1 plus I root 3, here we get minus 1 plus I root 3 plus 1 plus I. So cancelling minus 1 plus 1, we get I into root 3 plus 1. Now this is nothing but root of a square plus b square. A is the real part. Since there is no real part, we are having only the imaginary part, therefore root 3 plus 1 whole square. So square and square root will get cancelled, and therefore we get root 3 plus 1. The value of root 3 is 1.732. So plus 1 will give you 2.732, and this is certainly greater than 2, which is a given radius. And substituting the other singular point z equal to minus 1 minus I root 3 in the curve, we get minus 1 minus I root 3 plus 1 plus I. So here minus 1 plus 1 will get cancelled. Now take minus I outside, minus I into root 3 minus 1. And finding the value, which is equal to a square plus root of a square plus b square. Here it is a root of 1 minus root 3 the whole square, and therefore which is equal to 1 minus root 3, and that is equal to minus 0.732, which is less than 2. Therefore z is equal to minus 1 minus I root 3 alone lies inside C. The other point that is greater than radius will lies outside the C. So therefore the given f of z can be written in the form z plus 1 by the singular points are, we know, minus 1 minus I root 3 and minus 1 plus I root 3, and therefore the denominator can be written in the form z plus 1 minus I root 3 into z plus 1 plus I root 3. And the point that lies inside the circle can be taken here, and the point that lies outside the circle can be taken as f of z. So f of z is equal to z plus 1 by z plus 1 minus I root 3. And therefore using the Cauchy's integral formula, this integral over C f of z dz is equal to 2 pi a into f of a. So a is nothing but minus 1 minus I root 3, and that point lies inside the circle, that is a. Therefore it is equal to 2 pi a into, we know what is f of z. So here you substitute z is equal to minus 1 minus I root 3, then plus 1 divided by denominator minus 1 minus I root 3 plus 1 minus I root 3, and therefore minus 1 plus 1 will get cancelled in the numerator. The denominator minus 1 plus 1 will get cancelled. So we get minus 2I root 3, and therefore on simplification we get it is equal to pi a. Next problem, evaluate using Cauchy integral formula, integral over C z minus 3 by z square plus 2z plus 5 dz, where circle is given as a modulus z plus 1 plus I is equal to 2, another circle is modulus z is equal to 1. So first let us take the circle modulus z plus 1 plus I is equal to 2. So here the center is minus 1 comma minus 1 and radius is equal to 2, and let us find the singular point just by equating the denominator to 0. Therefore we get the singular points minus 1 plus or minus 2y. So z is equal to minus 1 plus 2y, and z equal to minus 1 minus 2y are the two singular points. And substituting these two singular points on the curve modulus z plus 1 plus I is equal to 2, we see that the first point minus 1 plus 2y plus 1 minus I. By cancelling minus 1 plus 1 we get modulus I, and modulus I is equal to 1, which is less than 2. So this implies this point, singular point, lies inside the circle. Then substituting z is equal to minus 1 minus 2i in modulus z plus 1 minus I equal to 2, we get it is equal to minus 3a, and that is equal to 3, which is greater than 2. Therefore certainly this point lies outside C. Therefore the denominator which can be written in the form singular points, and the point that lies Outside the circle can be taken as f of z. So f of z by z plus 1 minus 2y dz is equal to 2 pi a into f of a. A is nothing but minus 1 plus 2y. So here f of z is equal to z minus 3 by z plus 1 plus 2y. And therefore on substituting we get the value to be equal to 2 pi a into f of a. Then it is equal to pi into minus 2 plus I. Now the second circle equation is mod z is equal to 1. Substituting the singular points z equal to minus 1 plus 2y, z equal to minus 1 minus 2y in the given curve, we get the first point minus 1 plus 2y is substituted for z, which is equal to root of minus 1 whole square plus 2 square, and that is equal to 1 plus 4, which is equal to root 5, and this is certainly greater than 1, the given radius. Substituting the second point z equal to minus 1 minus 2y in mod z is equal to 1. We get minus 1 minus 2y is again equal to root 5, which is greater than 1. So both of the singular points lies outside the circle. And we know that if a function f of z is analytic at all points inside and on a closed contour C, then the value of the integral is equal to 0. Hence, in these two cases we get integral value is equal to 0.